All right, welcome Calc 1 students. So here we go, we're looking at what are called related rates. And so we're going to take a look at example number 1 now. You would have the upload that I sent with the PDFs showing all of the different examples. So hopefully you can see this, and but if you would just take a look at example 1 and familiarize yourself with the question. And again, at any time if you need to pause, so that you can catch up to whatever I'm doing. I will do my best to take my time, but it's hard to get a sense of how fast to go here. But anyway, as you see in example 1, it mentions a spherical snowball. So I will do my best to draw a picture of a sphere. As you know, that would look like a ball. And so that's just a perfect picture of a sphere, as you can tell. So, give Mr. Soccer Mom a break. I'm doing the best I can here, as I'm sure you are as well. But the one characteristic of a sphere that would describe that sphere in its entirety would be its radius. So let's go ahead and label the radius here as being this distance here. And again, I'm hopeful that you'll be able to see this well enough. So anyway, as you read this question, you will notice that it says that the sphere is melting. So just think about this thing as a video. And we're going to talk about how, this is an interactive thing that's occurring real time. But anyway, that sphere is shrinking as it melts. And so let's get into it a little bit here. You also would have the notes page already filled out. We don't need to pause for you to write these things down. So just take your time to try to understand them. But we obviously want to try to form an equation that would be related to this situation. And it's obviously talking about the volume of a sphere. Now, the equations that we'll talk about could come from all kinds of different things. It could be a geometry formula. For example, here it's the volume of a sphere. So I don't expect you all to memorize every single geometry formula that's out there. And if you encounter a question of this type, you might have to go look it up. But anyway, if you go look this up, or if you have it in your head, you know that the volume of a sphere is 4/3 pi r cubed. So that'll be the base formula for this particular question, since it talks about a sphere and its volume. There's all kinds of other equations that might come into play as we progress through this. There would be the Pythagorean theorem potentially, and then I put etc. because it's an almost endless number of formulas that we might use to get the equation started, to get the question started. But anyway, once we have our relevant formula or equation in place, then, in my opinion, we should then figure out what rate is it that we want to determine. Because as this thing shrinks, we're talking about the rate of change in volume as well as the rate of change in the radius. All right, those two characteristics are related as to the rate at which they are changing. And if we go back and look at the question here, which again, you have the printout, and hopefully you can maybe still see it here, but it says that they want to know at what rate is the radius changing. So we want to figure out how fast is the radius of this thing changing as it shrinks. So I always like to write down what it is we wish to find. And in the language of calculus, we're talking about the change of radius as it relates to time. So you'll get used to this. The symbol for that will be the change in radius with respect to time, written in calculus formula, calculus language as dr dt, change in radius with respect to time. And I will simply tell you that the examples that we'll be doing in this unit are all going to be with respect to time. How fast is something changing with respect to time? So anyway, that's the rate that will be determined, and that'll come into play much later. So as we progress, let's go back to the steps that we've provided for you. And again, you would hopefully find these on the PDFs that I sent you. But see, if we're going to find the rate of change of the radius with respect to time, ouch, right? That would be the motivation, that would be the impetus for us to differentiate this base formula we set up with respect to time, with respect to the variable t. And this is where our discussion about implicit differentiation would come into play. We did cover that before we went off on spring break. So anyway, if we differentiate this with respect to time, All right, so the derivative of the change in volume with respect to time, that's so important it's being done with respect to time, well, that symbolically would be written as dv dt. All right, and then when we differentiate the other side, again, with respect to time, ouch, what we need to realize is that this number, this is all a coefficient here. This is just a number being multiplied by a variable to a power. Now, as I suggested to you before spring break when we did implicit differentiation, I often try to show people to think of that r as being in parentheses. So if we think chain rule here, the idea would be we have a coefficient times a variable to a power. So of course the first thing would be to apply the power rule, whereby we bring this 3 down and multiply it by the existing coefficient, which in that case, this 3 we're bringing down would cancel the 3 here. So that would become 4 pi r squared, right? Remember the power rule, where we bring down that power and then decrease it by 1, all right? So that's doing the outside operation when we think chain rule here. And then when we go inside the parentheses, so to speak, and take the derivative of r with respect to t, that would create a dr dt tacked on the end of here. So again, I would emphasize to you to think chain rule here. You did the power rule because it was external, and then after that, you did the derivative of what's inside with respect to t. Ouch, I gotta quit doing that. All right, so there we go, we've got this new equation. And this relates the rate of changes of these two variables, the change in volume and the change in the radius. And that's again why this is called related rates, because the rates of change of those two variables are related to each other. Once we've done this, then we'll go back and read the question, and essentially we will replace certain variables in that equation with numbers, and we'll solve for whatever the unknown is. Now I would point out we've already determined that the unknown here that we wish to eventually determine is dr dt. So this will remain a variable, and every other variable we should be able to determine numbers from the narrative. So if we go back to the question and start reading this, all right, it says, let's look for some numbers here. It says that the volume is decreasing at a rate of 2 cubic centimeters per minute. All right, look at that. So cubic centimeters would be a volume measurement, and minutes would be a time measurement. So look at that. That's the change in volume with respect to time, which in this example would be dv dt. So that 2 there would be the change in volume with respect to time. That'll go in right here for dv dt. Here's another very important aspect of this. If a particular characteristic is decreasing, if it's shrinking, we need to realize that that rate of change, in other words, the word decreasing, because remember this snowball's melting, we need to remember that that volume would have a negative rate of change. So that would be decreasing 2 cubic centimeters per minute. All right, so there's a number to plug in for that. 4 and pi, those are constants. All right, if we keep reading, it says at what rate is the radius changing? That would be the dr dt that we're looking for. At the instant when that radius is 10 centimeters. So what I like to tell people is that as you're looking at this, you need to pretend this is a video of a snowball shrinking. And what we just did is we pressed the pause button on that video at the instant when that radius was 10. And therefore that would be the number we'll plug in for r right here. So we plug in 10 for the radius. And of course, as mentioned earlier, the dr dt will be our variable. And now it's a matter of algebra. It's just algebra, right? And again, as I've suggested to you throughout the entire semester, once we get to the snobby, it's just algebra, you know, then Mr. Soybean up here is going to just have to kind of run through the arithmetic quickly with you. So anyway, to continue that, I would suggest we go ahead and simplify all that right there. And again, following the order of operations, 10 squared would be 100. 100 times 4 pi. This would be 400 pi dr dt. And again, I'm a little unaccustomed to the setup here, so I apologize in advance. But if we go on and solve this, again, since that's multiplication there, we would divide both sides by 400 pi. And again, this is the part where I have to be a snob and say, this is just algebra. So then if we transfer this over here, we would see that we're left with negative 2 over 400 pi. I don't need an equal sign there. Negative 2 over 400 pi eventually equals dr dt. Now here's the thing too, that would reduce, in other words you could cancel a 2 and so forth, but what I'm going to ask you to do is to go ahead and put that in a calculator and we'll get a decimal approximation for it. So in other words, if we just grab the calculator and again, I would always suggest that when you divide, it's always safe to put the numerator in parentheses, divided by the denominator in parentheses. And again, this is all mechanical stuff that we've talked about in previous discussions. So if you change that into a decimal with the calculator, and again, it's arbitrary where to round it, so let's not split hairs on that, but let's call this 0.0016. All right, and then the other aspect of this that I would ask you to remember to do is to put the correct units of measurement on this. And it should help you to do that if you just look at these and think about how would a radius be measured in this case. And if you look at it, since a radius is a length, it's mentioned here centimeters. So centimeters would be the appropriate unit for radius per, see the symbol itself will help you figure out what label to give it. So radius would be expressed in centimeters, and then you read the question to see how time is expressed, and it mentions minutes. So at that instant, when that radius is 10 centimeters, the radius is changing at a rate of this many. It's shrinking because of negative. It's shrinking by this many centimeters per minute at that very instant. So there's our first example, and I hope that went all right. And again, I invite you to hit pause whenever you need to if I get going too fast. We're all learning here, and as a matter of fact, this was my very first attempt, so let's hope it went well. All right.